Okay, we're just going to take a quick look at another audio switching device. The idea of this device is that you can inject an audio signal through this XLR lead or connector, and then have that route through to the corresponding pins on this RJ45 that matches a Vipedia audio output wiring. So this can plug into the bottom of your NTI meter or any other signal generator with an XLR connector, and then this would connect into effectively the lead that would normally plug into the back of your Vipedia. You would pull that out, plug it in here, because that then goes off to your amplifiers, that lead. So whatever you inject in here is then getting routed to any amplifiers that are wired onto whatever audio output you've selected by this board. And by doing that, you can watch the little dB gauge on the amplifier to see which ones fire up. So you then know output 1, for example, is routed to that amplifier and that amplifier, but not the others. Okay, so it's a way of verifying which amplifiers are wired to which outputs. All right. I've had to shove a little wire in there just to give me a ground reference, only for testing purposes. You don't need to do that. The ground is basically pin 1 on the XLR, and the other 2 are the hot and the cold signals for the balanced audio. So before we do this, what we want to do is to make sure that the routed audio that comes from here out to here is not really affected by this board, that it doesn't introduce a load of noise or affect the signal level. That's called the fidelity. It's the trueness of the originating source. So if your output is exactly matches your input, then that's 100% fidelity. Okay, so what we're going to do is just take our NTI meter and just connect in an XLR lead. We're going to mute that to start with. All right, it's set to, you can't see because the backlight's just come on, but it's set to 1 kilohertz tone, and it's at 0 dBV. So dBV is a reference to 1 volt, so 0 dBV is 1 volt RMS. All right. So we plug in the XLR lead there, and then from the oscilloscope we're going to take our first input. We connect the ground to the ground reference, is there, and we'll connect. Need to put our probe end on. We'll connect this probe to the hot or the positive, and we'll connect the second input, which is the blue trace. We'll connect that to the cold, or called the negative, there. You don't have to do this on the oscilloscope because all the grounds on probes are actually commoned up normally, but I will do it because it helps with the trueness of the signal. Okay, it helps reduce the noise being picked up by the probes and everything. So there we go, that's connected. So now if I unmute the signal generator, so that's now sending. And then over on the scope, if I turn on my channel 1, now I find this on these NTI meters, when you turn them on and off, the ground reference shifts up and down. So you can see it now settles back down to the ground reference. I don't know why it does that. And then channel 2, if we turn that on, there you go, you can see that is a balanced audio signal for a 1 kilohertz sine wave. So I'm getting 1 kilohertz reading down here. And the blue is exactly the inverse of the yellow. So the amplifier takes a differential input and amplifies it. So it will take the difference between the yellow trace with the blue trace, the hot from the cold or the positive from the negative. It's a bit odd calling it negative because it's AC, so it goes negative, positive on both legs. So I think that's why they come up with the hot and cold phrase. What I can do on the scope now is basically do a mathematical trace, which is doing exactly that mathematics. It's deducting this from this. So this red trace here is not an input at all, it's mathematically calculated. If I go into math here, you can see it's channel 1 minus channel 2, and that's what's being displayed. Okay. Now what I want to do is record that as a reference. So if I just click on save, and I want to save to reference 1, okay, and then click save, that's it, it's now saved. All right, we'll get rid of that, and we'll turn off our channel 1 and channel 2. Turn the maths off, I think that's off. Yeah, and then we can bring back up the reference. There we go, that's what we saved just now. So that's what we're going to use to compare against, that mathematical differential signal. So let's just mute this again. There we go, we get rid of this connection now. Unplug all that, and we can get rid of that. So this now plugs in the bottom of into the XLR of the NTI meter. There we go. And then, in order to be able to stick my probes into here, the easiest way is to use a BOA, all right? You know, standard ASL BOA board breakout adapter. So if I plug this RJ45 in here, each pair in here comes to the corresponding pairs on this BOA now, so I can sniff off the signal with my probes. In order to do that, I'm going to have to take these little clip adapters off. Alright, now I need to connect to the battery ground, which is here. I will connect both. I will connect both, yeah. Hopefully that will hold. Okay. So I'm going to turn this device on. You can just see the LED down here. I think if I click it once there, I'm on output 1 basically, which on the BOA should be presented on these two first pins there. So if I turn on the yellow and blue signals, channel 1 and channel 2 on the scope, and I connect in the yellow. Let's unmute the meter, there we go. Now that will come down, as I say, it does that NTI meters. I think it's capacitance or something in the meter, it goes to an offset above its own ground for some reason. So you have to be careful with that. And then the blue probe, or the second channel, we connect there. There we go, that's exactly the same as we had before in terms of the balanced audio signal. One is the inverse of the other. Now I had noticed this previously when I did a check, in that I've got all of this noise going on around there, and that was concerning really. I don't know if you can see that on the video, but there's loads of little spikes, and it turns out to be this Cat5 cable here is basically intertwined with my LED lights. If I turn the LED lights off, all of that noise just disappears. So that's all it is. It's just noise picked up by my LED light. Okay. And then if I turn the maths trace back on, there we go, look, it's bang on, overlays exactly the reference. If I click to reference, bring that on top. Oh, it doesn't bring it on top. I've probably got to turn it off and then back on. There we go, then it's on top. And if I press maths, then the red trace you can see is sitting exactly on top of that grey one behind. Okay, so that is good. It's true to the original signal. Okay, let's just disconnect all this now. Okay, that's that disconnected. I'll turn the scope off. Channel 1, channel 2. Turn that reference off. There we go. We can unplug that now. And we'll disconnect it from there. Okay, so hopefully you can see that. So yeah, that's the XLR, which is the audio input, and that's the RJ45, which is the output. So how does it get from there to there? Well, on the board here, there's a basic circuitry. I'll just get something to point with. There we go, screwdriver do. Got a little on-off switch here, and we've got a push button here, momentary push button, and that feeds into the clock of this chip here, and the first input clock, and this is called a dual JK flip-flop. So when we press that button, the first output of this will toggle on and off in a latch state, and then that feeds into the data of the secondary flip-flop. So the second flip-flop will toggle every other press of the button. So effectively you get a binary signal of two digits. And that binary signal feeds into these fellas. This one is a single channel multiplexer, and this one's a dual channel multiplexer. Depending on what your binary 0001, 10 or 11 output is from here, it will then route a common input to any one of its common outputs. This is single channel and this is dual channel. This single channel one is just merely driving these LEDs. It's only using the first 4 outputs of this. This dual one is what's switching the audio hot and cold inputs through this chip out through to the RJ45, but it's switching 2 legs at a time, so it's using all 4 dual multiplex outputs. So when you press the switch, it will just route through. It's a bit erratic, because I've got a bit of bounce on this cheap switch. Okay, but basically you go through each of the outputs in that way. And that's about it really. Just runs off of 3 AA batteries, so 4.5 volts, should last ages. It's hardly any current. So hopefully that saves a bit of time, and we can be confident that we know which amplifiers are connected to which output. All right, catch you later.